This is the chapter 3, pressure and fluid statics from the textbook. We will not be covering all the topics from this chapter. Instead, our main focus will be on pressure and manometers. Now about fluid statics. Fluid statics deals with fluids at rest. Since the fluid has no macroscopic motion, shear stresses are absent and the analysis is governed mainly by normal pressure forces and body forces such as gravity. The main objectives are to define pressure, distinguish between absolute, gauge, and vacuum pressure. And we will also touch up on concepts like manometers and barometers, which are pressure measuring devices. The pressure may be reported using different reference levels. Absolute pressure is measured relative to absolute vacuum. P absolute is equal to 0 at perfect vacuum. The gauge pressure is measured relative to local atmospheric pressure, which means P gauge is equal to P absolute minus P atmospheric pressure. Most pressure gauges read gauge pressure because they are calibrated to read 0 when exposed to atmosphere. So that means when next time when you see a pressure gauge at 0, that's not actually equal to 0. That is the atmospheric pressure. Or otherwise it is called, it is including the atmospheric pressure. The vacuum pressure is used when absolute pressure is below atmospheric pressure. P vac is equal to P atmospheric pressure minus P absolute. So this particular figure can be an easy tool to understand these relations. Here the red line indicates the P atmospheric pressure, and if the pressure is above the atmospheric pressure, then the gauge will read P atmospheric pressure plus the gauge pressure. So whatever you see in the gauge is actually equal to the gauge reading plus the atmospheric pressure. Now if the pressure is if the absolute pressure is less than the atmospheric pressure, the gauge reading will be the difference between atmospheric pressure and the absolute pressure. So in most of the problems that we encounter, the equations and all, the pressure should be interpreted as absolute pressure unless stated otherwise. So in any problem that was given in fluid mechanics or thermodynamics, you should assume that is absolute pressure. If it is not, then it will explicitly tell you that it is gauge pressure. Now pressure is defined as normal compressive force per unit area. Although pressure produces force, pressure itself is not a vector. It is a scalar quantity. At a point in fluid at rest, pressure has the same magnitude in all directions. The pressure force always acts normal to the surface on which it acts. But the pressure magnitude is independent of surface orientation. Therefore, for a small fluid element in static equilibrium, Px equal to Py equal to Pz is equal to P, which means pressure in all directions is equal to the same pressure. This result is fundamental for fluid statics and allows pressure to be treated as a scalar field. Now we will take a look into the wedge-shaped fluid element, which means you have a fluid element under consideration which has a cross section of triangle if you slice it vertically, and the y-axis is going towards the screen. Only x and z axis is displayed here. So that's why it is called as a wedge. It has a depth associated with it, which is equal to delta y. Now, if you start to analyze the pressure and forces acting on this element, you can obtain the force is equal to pressure times the corresponding area. For example, for the force along the x-axis, because of P1, you can multiply the pressure P1 with the area of cross-section along the x-axis, which is delta y times delta z. The same thing goes for the pressure 2. So similarly, if you do the force balance, let's take a look. Along the x direction, sigma fx is equal to m times ax equal to 0. Since it is in static equilibrium, the acceleration is equal to 0. So sigma fx equal to 0. Now this means for this particular pressure, you will have that whole component acting along the x-axis. So that's why this is written as a whole, and it is actually acting towards the positive x-axis. So that's why it is positive. Now P3, the force corresponding to P3 can be split into two components, one vertically downwards and along the negative x-axis. The component corresponding to the negative x-axis is resolved into P3 times delta y times L times sine theta. So with that, you can balance that equation along the x-axis. Similarly, for z-axis, you can obtain this way. Now, when you do the z-axis balance, you have the gravity, and gravity is acting to the negative direction of the z-axis, and you will obtain the body force, which is density times volume, which is mass. So mass times gravity, which is the weight, which is the force acting because of the gravity. So that can be obtained using this relationship. So that also will come into the balancing term in z direction. Now, if you carefully look into the equations, we can use the geometry to simplify these expressions. For example, delta c is equal to L sine theta, and delta x is equal to L cos theta. So if you substitute delta z equal to L sine theta, this whole equation will become P1 minus P3 equal to 0. So because delta y times delta z will become delta y times L sine theta, and the whole term will be can be taken out and it will vanish. Similarly, for z-axis, delta x can be substituted with L cos theta. Here also you will have delta x can be substituted using L cos theta. So that together with delta y, you can take it out and you can divide it from the whole equation. So what you will get at the end is P2 minus P3 minus half rho g delta c equal to 0. Now at this stage we will make an important assumption, which means the size of the wedge element will become infinitely small. So in case if this wedge element collapse to one particular point, then the dimensions will change. For example, the theta will become 0, or it will tend to become 0. When theta tends to 0, delta z will tend to 0. So because of that reason, this particular term on this equation will become 0. So that means P1 minus P3 equal to 0 means P1 equal to P3, and P2 minus P3 equal to 0 means P2 equal to P3. Because of that, we will get P1 equal to P2 equal to P3 equal to P, one specific value. Now this is how we prove that pressure at a point is same in all directions. Now for static fluid, pressure varies with elevation according to hydrostatic equilibrium. The differential pressure relationship is delta P equal to P2 minus P1. which is equal to minus rho g delta z. So if you look into this particular image, you have depth of the water, you have fluid, and the pressure will increase as you go to the bottom of the water, and that pressure variation is given as minus rho g delta c. Here z is positive upward, therefore pressure decreases with increasing elevation and increases with depth. For constant velocity, p well below is equal to p above plus rho g delta c, which is equal to p above plus, you can combine rho and g with specific gravity, so that's specific gravity symbol over here. So that's another way to look into it. And the specific gravity becomes is a very powerful tool for manometer analysis, so this equation has to be studied well. Now for liquid which are open to atmosphere, you can write P is equal to P atmosphere plus rho GH, or you can combine P and P atmosphere in this format, which is P gauge is equal to rho GH, where H is the depth below the free surface. Now if the fluid has variable density, this same expression will change it into this integral form. Delta P is equal to P2 minus P1 is equal to minus integral of Z1 to Z2 rho G dz. For liquids, density is often treated as constant. For gases over large elevation changes, density variation may need to be included. In gases, the density is relatively small. Therefore, pressure variation over ordinary room scale heights is usually negligible. For example, in a 5-meter high room, the pressure change between floor and ceiling is very small relative to atmospheric pressure. Thus, gas pressure in small enclosures is commonly treated as uniform. In liquids, pressure variation with depth is significant because liquid density is much larger. The pressure at depth h is h below a free surface is P equal to P atmospheric pressure plus rho GH. The pressure also remains constant along horizontal plane in the same connected static liquid. For example, if you look into the bottom figure, you'll have different points like B, C, D, E, F, G. So at all those points, it lies in the same elevation. Because of that reason, it has same pressure value. It doesn't matter whether the geometry is irregular, but if it is connected by the same fluid, then it should experience the same pressure. Now, the points like A and this particular point H will have different pressure values. Now, this has a very important application going forward. Because if you want to solve the pressure variation in a manometer, this particular feature is really helpful. Pascal's law. The Pascal's law states that pressure applied to a confined liquid is transmitted undiminished throughout the fluid, which means if you have, for example, if you have a fluid contained system like this, and at one end you have a piston applying pressure, and on the other end you have hydraulic jack which is lifting the car. Now in this case, the pressure inside the container at every point should have the same pressure. Now, if you apply the force on one end and increase the pressure, then the similar amount of pressure will increase on the other side at the similar location. So, mathematically, that means if the pressure exerting at this particular point 1 is equal to P1 and P2 is exerting at P2, we can use the leverage mechanism just by force balance. You can multiply pressure with area to obtain the force. So if the area is small, you're applying only small amount of force, and on the other side you have larger area, and with lesser effort you can lift the car. And that is called the ideal mechanical advantage, the ratio between A2 and A1, and that can be also related with the force and the pressure in the same manner. So that's called Pascal's law. Now the lower section shows a barometer. Barometer measures atmospheric pressure using liquid column, commonly using mercury. At equilibrium, atmospheric pressure will become equal to the weight of the mercury column, which is rho times G times H, where rho is the density of the barometric fluid and H is the column height. The cross-sectional area of the tube has no effect on height of the column, provided that the tube diameter is large enough to avoid the surface tension, which means you should not select a tiny diametered tube for these type of measurement devices, because the surface tension effect will dominate the readings. So you have to use slightly bigger tubes, not too big ones, but tubes which are usually available in Home Depot or something should be good enough to measure or to get rid of it, to be used as a barometer. You don't get the effect of surface tension dominated over there. A manometer. So manometer is a device which is used to measure the pressure differences using hydrostatic height difference of a fluid column. For a basic U-tube manometer with one side open to atmosphere, the pressure relationship is P2 is equal to P atmospheric pressure plus rho GH. So what they are doing is, it's a very clever invention. If you want to measure the pressure of the gas, you can balance the pressure by using this manometer. What it does is, this gas will try to push the liquid against the atmospheric pressure, and the atmospheric pressure will act backward and they will balance and will find the equilibrium position. Let's say if this is the equilibrium position, the pressure at the point 2 can be obtained by the relationships that we discussed so far, which is height of this column multiplied by the specific gravity of it, which is rho GH, plus atmospheric pressure is acting on this free surface. So that together will give you the pressure at point 2. And because of the pressure continuity at the same level for the same fluid, P2 will be equal to P1. That way we got this much. And since gas is having very less density, we can assume P1 is the actual pressure of the gas. Now an inclined pressure measurement device is called an inclined manometer. Sometimes what happens is the basic manometer is difficult to use for tiny variations in pressure. So if you want to increase the accuracy, instead of measuring the vertical height, you can measure the inclined length. So that way, for a same elevation change, you will get larger lateral changes. So we can increase the accuracy of measurement by using this simple inclination for the tube. So that type of manometers are called inclined manometers. So you will see these devices in industries, especially like if you are installing radon fans or something in household, that this will be definitely used in there to understand if there is a flow happening within the system. And also you will see this in the thermofluids lab later on in your course. For multiple immiscible fluid layers, for example, like if you have different type of fluids stacked on top of each other, which are not mixing each other. So in such type of liquid layers, the pressure increase across each layer is just specific gravity of that fluid multiplied by the height of that liquid. For example, in this case, the pressure at the point 1 is equal to pressure at atmospheric pressure, which is the free surface pressure, plus rho g h1, and rho is the density of fluid 1, and rho 2 g h2 plus rho 3 g h3. That will be the total pressure at point 1. So each term of each term shown here will correspond to the representation corresponds to the contribution of hydrostatic pressure to one liquid layer. The lower section shows a differential manometer which is used to measure pressure drop across the flow section. So in the previous slide we looked into inclined manometer, which is used to measure the pressure inside a chamber or a pipeline. But if you want to know the pressure drop across a particular section, usually you can test the pressure drop of valves, and there are different flow devices which you want to do make sure it has a least pressure drop. So to understand that, the easiest way is to either connect pressure gauge over here and another pressure gauge over here, or the other easier way is to use this differential pressure manometer. The pressure balance equation will become equal to P1 plus rho g a plus h minus rho 2 gh minus rho ga equal to P2. So this is how the analysis goes in here. So this is a easier way to look into these type of analysis. You can start analyzing the pressure starting with one particular point. Let's say we start from point 1. So the pressure at that particular point is P1. Now if you go into if you go downward, the pressure will increase, because if you go downward in a fluid, the hydrostatic pressure increases. So depending upon the depth, so from point 1 to A, the depth is A plus H. So within that much depth, the pressure increases P1 plus rho g times A plus H, and that's what this particular term. Now the same pressure is applicable at point B. Now from B to the next point, we have a reduction in pressure, because if you go from the bottom of the liquid to upward, the pressure should be reduced because pressure increases with the depth. Because of that reason, you will have rho 2. Now we have a different liquid in here. Because of that, you have rho 2 multiplied by g times h. H is this differential change going upward. Now it doesn't stop over there. That is the pressure at this particular location. It should go further upward. So if it has to travel further upward, we need to subtract that much pressure, which is rho times, this time it is the density of the water, rho times gravity times A, and that's what they do with this particular term. So that collective arithmetic operation should give you the pressure at point 2. It's that simple. Now if you rearrange the terms, P1 is usually higher than P2 because the pressure will lose over the length, and that difference is equal to, rearranging these terms, rho 2 minus rho 1 times gh. So uh, if you measure the height of this variation, you can estimate the pressure drop. So that's how this device will become very convenient, because the density or the specific gravity of both of the liquids will be already known, and you do not need to know the pressure at 1 and pressure at 2 at all. Instead, if you just by looking into the reading, how much they actually differ with each other, we can directly estimate the pressure drop. So it's a very beautiful, convenient device. And there are other pressure measurement devices also. It can be mechanical or it can be electrical. One of them is a classical invention called Bourdon tube. Bourdon tube consists of a hollow metal tube bent like a hook, whose end is closed and connected to a dial indicator needle. What it does is, whenever the pressure goes into that tube tries to straighten up. In that due course, if you connect a gear with it with a needle, that straightening will change the needle reading, and that way we can calibrate the needle movement with respect to the pressure values. Pressure transducers use various techniques. It will convert pressure induced deformation into electrical signal, such a change in voltage, resistance or capacitance. So using that, you can calibrate and convert that into equivalent pressure values. Another option is to use strain gauge, and strain gauge pressure transducers use a diaphragm that deflects under pressure. The restraining strain is measured electrically, and then it can be converted into mechanical analog pressure. Piezoelectric pressure transducers use crystalline materials that generate electrical potential when subjected to mechanical stress. These devices are selected based on pressure range, accuracy, sensitivity, response time, durability, and etc. So there is no universal one size fits all solution. Instead, depending upon specific application, you have to choose the corresponding device based upon your experience. So that should cover the main components of this chapter. The main equations, you saw what type of equations will be used for problem solving, and we will do more problems in the class.